Okay. All right. So first thing first, I'm going to start with the logisim file for the subtractor. Okay. All right. So several things I need to do, because I cannot remember all the equations. So I'm gonna start up the browser, just so that I can refer back to T1, T2, T3. What those equations are supposed to be. And the browser is over here, and I can just restore. So instead of using the subtractor, well, I need both slides. I need both the subtractor and the adder. So I'm going to pop open the adder and also the subtractor as tabs. What I need from the adding is in section 6, it talks about K1, K2, and K3. Those are the equations that I need to implement in the subtractor as well. Okay, so this is the adder, and here are K1, K2, and K3. So I need these three equations from the addition. And then the subtraction one is pretty easy. I just need to know how to define P and G in the subtractor. So if you go to look ahead and go through the derivation, then you can see the way we define G is just negating the X. The way we define P is just negating the X as well, compared to the P's and the G's for the adder. Okay? So if you already have the adder implemented, you can really just change the OR gate so that the X input is negated. Okay? Even if you were to use individual gates for each P and each G, there are only 6 gates individual. You just have to negate one of the inputs for each of the 6 gates, change the labeling, and you're all done. Okay? But that's not what I'm trying to demonstrate today. What I'm trying to demonstrate today is to use multi-bit as much as possible, and then so that we can have a design that looks really clean. Okay, so now we can go ahead and start up the startup logisim, Java -jar downloads logisim generic. There we go. All right, so let's go ahead and zoom in a little bit, and then we'll have the multi-bit inputs and the single bit input here. The single bit is our borrow in, which is also known as T0. To 2 other ones, each one is 3-bit, and the first one is X. Now, if you really want to make it clear, this is also the minuend, and then the other one is Y, which is also our subtrahend. Okay, so those terms are really useful because you can tell which one is being subtracted from which one when you look at the minuend and subtrahend. Okay, so I want to stay in multi-bit mode as much as I can. So the first thing I need to do is to generate the P and the G terms, and that can now be done by just going to the gates, pull out an AND gate, pull out an OR gate. The AND gate is for the G terms, and I want this to only have 3 data bits, but only 2 inputs. Okay, and we can make this narrow because it doesn't need to be that big. So we also want to negate the top, which is where the X is coming in, and then the bottom is where the Y's are coming in. So this is how we set up all the G's. One single multi-bit gate is now doing the job of 3 individual AND gates. And I don't need a splitter, okay? Because I don't need to split X and Y ever in this entire design. The X and the Y's do not need to be split at all. The G's and the P's, on the other hand, well, you can either split it here or you can split in the sub-circuits. It's up to you. So we'll do the OR gate, same thing. Okay, 3 data bits, 2 inputs, and make it narrow. There we go. So same thing, we have the first one coming in from the top. Oh, okay, I forgot one thing. I forgot to negate the top one first. So we'll negate the top one, which is coming in from the X, and then the bottom one is coming in from the Y. That may not be a good idea. There we go. Better. There we go. So now we have the P and the G terms defined, without using a splitter at all and using only 2 gates, which is kind of cool. Are there any questions about this part? No questions about this part? Okay, if there are no questions about this part, then I'm going to work on K1, K2, and K3. Okay? So K1, K2, and K3, they all depend on the G terms, the various G terms, various P terms, and K0. Okay, so those are the common interface to all of those individual parts. So what I'm going to do is I'm going to start a new design, new circuit, and we'll just call this one K1. Okay. So there are several ways to do this. If you want your overall design to look exceptionally clean, okay, this is what you can do. You can have the 3-bit inputs and then do the splitter inside the sub-circuit. Okay, so that's one way to do it. And then the last one is going to be a single bit, which is K0. So these do not need to be labeled because I did not specify whether you should label your the pins of your sub-circuits or not. You don't have to label those, but I'm going to label mine because I need to know which one is which one. There we go. This is K0. So when you go back to the notes, K0 or T0, they work exactly the same way. It's just G0 plus or P0, K0. Okay, so with this one, there's no way to avoid a splitter. Okay, so we can go ahead and do a split here. You can either split early or you can split late, but either way you need a splitter. But the splitter can be very specialized in this case because I only need bit 0 out of the P and the G's. Okay? So that means I can make my splitter so that the fan out is just 1 and the bit width is 3, and then the top bit is the only one that I need. The rest are none. In other words, I'm taking a bundle of wires, I splice and take only bit 0 out. The other bits are just terminated. They're not doing anything in this particular design. I'll duplicate it because I need this for both the P and the G's. So we need one for the P. Whoops. Move. There we go. We need one for the G. There we go. All right. So now we can just go ahead and implement the gate, which is an AND gate between P0 and K0. So we pull out an AND gate. Two input, narrow, and that's between P and K. There we go. And then we need an OR with the G. Okay, so we pull an OR gate for the G, turn this into 2 input, narrow, and then the output is a single bit, so we have a single bit output, which is our K1, so it's good to label this one as K1, but this entire circuit is K1. Is that okay so far? Okay. So now we right click on K1, edit circuit appearance. That's fine. We just leave it the way it is. Might be helpful to label it, so we'll just label this one as K1. And if you want to, we can also label, the G's are the ones, the first ones, and then K0 is the last one, and then the one in the middle is P0. All right, so we got another circuit done, and then we go to project, add another circuit, which is K2 in this case. Basically the same deal. Okay, since it's kind of the same deal, we go to K1, and then we just kind of copy some of the circuits here. Control C, go back to K2, paste, because they are kind of the same. We can get rid of these extra wiring. The splitter needs to be changed because now we need the fan out ratio to be 2, and we need bit 0 and bit 1 as well. So bit 0 will be the top, bit 1 will be the bottom, bit 2 is none because I don't need it. So Control D, make a copy of that. So now we have bit 0, bit 1 of G G and P, and then K0 by itself. Now it's time to look up the actual equation. So G1 is by itself. We need P0, P1, and then K0 to be one AND gate. Okay, so we pull out an AND gate, make it a 3 input, and narrow is fine. There we go. So that's the last term. The second term, the middle term, is P1 G0. Okay, we can just duplicate an AND gate here, turn it into a 2-input AND gate. And the equation was G0 and P1. So we got G0 and P1 into this one. And then G1 is all by itself, okay, which is, it doesn't look very good, but you know, it's going to be okay. And then the overall OR is a 3-input OR. So we pull an OR gate here, turn it into a 3-input. Oops, that's not the right one. There we go. 3 input. One goes here, one goes here, and one goes here. And then the output is our K2. So we'll take a little output pin, label this one as K2, and then we can go back to the circuit, edit circuit appearance. It looks exactly the same as the other one, doesn't it? This is K2. The top pin is G, bottom pin is K0, and then output pin is just K2, which is already labeled, so we don't need to relabel it. Okay, so second subcircuit done, third subcircuit. And another circuit, which is K3. So we go to K2 and go, let's borrow something from here. So select all of these, copy, oops, that's duplicate. Let's Control-C, copy, and go to K3, paste. And this time we need the splitters to split all 3 ways. So that will be needed. Okay, just like that. And then we go back to the equation, which is here. And then we look at the most complicated one is the last term, which needs a 4-input AND gate. So we'll put it all the way down here. 4 inputs. Okay, the first one is K0. And then we need all of the P's. There we go. The second one needs 2 of the P's and 1 of the G's. Make it a 3 input and a narrow. Okay, so we need G0, P1, and P2. Okay, and then the next one is a 2-input AND gate. Oh, I got one too many. That needs G1 and P2. So we got G1 and P2 is this one. There we go. And then G2 is on its own, right there. And then we need one gigantic OR gate with 4 inputs to combine all of these wires. And one single output pin as our K3. Go back and edit the circuit's appearance. So this is K3, this is G, this is K0, and that's it. All right. So now going back to the main design, okay, we need to pull one of K1, one of K2, one of K3. And the nice thing, is, now I can just get all the G's and feed the G's into the G connector of all of these subcircuits. Take the P, feed the P, whoops, wrong one. Take the P and put it into, connect it to all the P connectors. And take B in, which is K0, and do the same thing. Is that okay? Now we need a merger to merge all the K's, okay, well not all, but 3 of the K's back into one single bundle. So we go back to wiring, go to splitter. We want it to face west this time because the split end is facing west. Want a 3 fan out of 3, that would be good. So the first one is K0, which is our B in. The second one is K1, and the third one is K2. There we go. So now we need the exclusive OR gates, but remember we can use multi-bit exclusive OR as well. So we now take the exclusive OR gates from within the gates, and it needs to be 2 input, make it smaller. The first one has to combine the X and the Y. So I'll make this one on top. Here's the X. And of course I forgot to change the width to 3 bits. And this is the Y. Okay. It doesn't look very good, but it looks kind of busy. Okay. And then we need one more of these to combine the result of XY and the borrow bits. So the borrow bits will go in here, and this is our actual output. This is the difference, which is a 3-bit output. And then we have one leftover borrow out, which is our K3. And that's the whole design. Okay, question is, does it work? Right? We need to test this thing. So 0 minus 0 minus 0 is 0 with no borrow. Okay, that's good. That's one test case right there. So what about 0 minus 1? Okay, let's try this. 0 minus 1 is 1, 1, 1 with a borrow. That's good. What about 0 minus 0 minus 1? It is also 1, 1, 1 with a borrow. So that's good too. What about 1, 0, 0 minus 1? It is 1, 1 with no borrow. So that's, it seems to me it's working. So, it looks good to me. So are there any questions about this particular implementation of a subtractor? So the overall design is cleaner, it doesn't have all the splitters, because the splitters are inside the K1, K1, K2, and K3 circuits. But how you want to do it is entirely up to you. Okay, so how you structure the circuit is not important, but as long as you're using the borrow look ahead mechanism, how you use sub-circuits to make your overall circuit look simpler is entirely up to you. Are there any questions? Now, because the introduction of a multi-bit gate is introduced and it is also covered in my actual instruction, it can appear in your exams. Okay, so in your exam, I might give you a question that has a circuit that has multi-bit gates, multi-bit input pins, and so on. And so you need to understand how this works. Even if your assignment is working 100%, get 100% of the points, and it's using individual gates, you still have to understand how a multi-bit gate works. Is that okay? Yeah. All right, cool. All right. So So if there are no questions about this, I might just stop the streaming engine, and so that you guys can just get back to today's assignment started. Okay. So with today's assignment, what you need to do is to look at the assignment itself, which is based on this template file. So when you look at this template file, I've never tried to click on a regular text file in Canvas before. So is it going to download it? Nope, it actually shows the content. Okay, very good. But using a kind of weird font here. Okay, so what you need to do is to look at this program and figure out what you want to put inside parse sci10, because that is what you're going to do, is to parse the input, which is already a string. PTR of parser, of P parser, is already pointing to the first character of that string. So you know the starting point already. Yep.
The last character, is it null?
It is null terminated, correct. So it is guaranteed to be null terminated, and I will only test your program using valid scientific notations. Okay? But it can be anything that is specified in the regular expression. So I will play by the rules, by the rules being the regular expression, but it can be any variation that the regular expression allows. So are there any questions about this particular homework assignment?
Do you say it could be any number, or it can be just same definition?
Okay, let's get back to the notes, because it is all based on the notes here. So when you go to the floating point representation notes, the regular expression that I put here tells you what can be the input of your program.
So also it's optional, so it can be like any digit, like 5 or 520, any digit, any 10-bit digit.
It can be 5, can be 5.0, can be 5.05, can be plus 5.05, can be negative 5.05, can be 5.05 E20, can be 5.05 E plus 20, can be E 5.05 E negative 5, can be, you can have leading zeros, okay? With the exponents, I can give you something like 5E05. Yeah, that conforms to this rule. Once you see the E, you can have an optional sign, and then this specifies at least one base 10 digit. 0 is a base 10 digit. It really should not need a special case, by the way. Okay, to handle the 05 is really the same thing as handling 552, 55, or whatever. Okay, it doesn't make any. You should not need special logic to handle leading zeros. Leading zeros are not problems. Okay? But the output has to be in the form of those 3 numbers. So your Mantissa 10 has to be an unsigned integer, and I strongly recommend that you specifically use a 64-bit unsigned integer. You can add additional include files if you want to, okay? But your file has to be a .c file. It has to be a plain C program, not a C++ program. All right? So I'm going to write up the actual assignment, but I might turn off the streaming at this point. So are there any questions before I turn off streaming? No questions? No question you want me to, no answer you want me to record on YouTube? Okay. All right, we'll stop the recorder.